In this video, we're going to look at the orientation factor and the orientation of molecules when they collide together. Previously, we looked at this collision model, but not every collision will result in a reaction. So we can sum up the last video by saying that only the more energetic molecules undergo reactions as a result of collisions. And we know that the energy of the collisions must be greater than the energy of activation. Another thing that we can say, and the topic of this video, is that the probability of a particular high energy collision resulting in a reaction depends on the molecular orientation during the reaction. And I'm going to use an example here to illustrate this. If we have two BrNO molecules, they can collide together to become Br2 plus 2NO. And there are three ways in which this molecule can collide. The first is, here we have ONBr and ONBr. So we have two molecules. If these molecules collide together in this fashion right here, then we can get a reaction, because Br2 is going to form and 2NO molecules can form. So if we have the collision right here, the bromines can break off, and then the 2NO molecules can break off. But what happens if this molecule is going this way and it hits the back end of another molecule? In this case right here, the bromine and the oxygen are not going to form a product. So even if we hit this with enough energy, the orientation here will not allow for a suitable chemical reaction. On the other hand, if I had this ONBr molecule and it's moving this way, and it came into contact with a molecule orientated BrNO, and it would be moving this way, then once again we can form the Br2 product, and then the 2NO molecules will separate off. Okay, so this is illustrating that the orientation will matter in a particular reaction, and there was a guy named Arrhenius who looked into both of these requirements, both the orientation factor and the collision model, to propose his theory of the rate constant.